Let's look at active power. That is megawatt output first. This is the power which actually does useful work for the consumer. For example, you use kilowatt hours in your light bulbs and electric heaters. You pay for kilowatt hours to run your appliances. The megawatt or kilowatt is the component of power which does the work. As we know, the demand for megawatts varies throughout the day as consumers switch their electrical devices on or off. As we cannot store electrical energy, at least in large quantities, the combined power output of all of the generators which are connected to the system must exactly equal the total power demand at every instant of the day. The total power demand consists of the consumer's demand plus power system losses, which may be as high as 4 or 5%. If at any time the power demand is greater than power production, then the frequency will fall. It is the load dispatcher's job to keep system generation and load balanced. He must do this while paying attention to the economic loading of units, which means the most economical generating units should be fully loaded first. At the same time, he has to allow for limitations in the transmission system, say due to line outages. So the load dispatcher's job is quite a handful, just as much as the turbine operator's. However, he is assisted by computer programming and by automatic devices such as the turbine governor and the dispatcher's automatic generation control system, known as AGC. We mention all this as background so that you can appreciate the dispatcher's urgent appeal to you on occasion for either a rapid increase or decrease of unit output. We know that in order to change the generator's active power output, we must change the energy input, that is, the steam flow through the turbine. This may be performed in several ways: manually by the operator in accordance with predetermined loading instructions or on request from the dispatcher; automatically by the turbine governor, which responds to changes in turbine speed, which is in turn related to system frequency; automatically by the dispatcher's AGC if this particular generator is being used for regulation, that is, to assist in frequency control. Most of the machines on the system, that is, steam turbines, gas turbines, and hydro turbines, will operate on governor control. If there is a sudden increase in system load, all of the machines immediately slow down, and this is immediately detected by the governors. Governor response opens up the fuel inlet or steam inlet valves and so increases the unit outputs in order to meet the increased load demand. This action takes about 10 seconds to stabilize. However, it is important to note that although each governor moves to stabilize the frequency, it does not return the frequency to its original position. This is due to the regulating characteristic which is built into the governor known as speed droop. Typically, the turbine governor is set to regulate at 5% speed droop as applied load increases from 0 to 100% power output. Of course, this situation can be corrected easily by adjusting the set point of the governor. This can be done by the operator at various intervals or by automatic frequency control devices. Usually, certain generators on the system are selected to operate as regulating units, receiving immediate signals from the AGC system to correct frequency. The objective of the speed droop setting is to ensure stable operation of generators which are connected in parallel on the power system. If all of the governors on the synchronized generators are set to, say, 5% droop, then they all share in load changes proportionally. However, we may wish to make certain units on the system more responsive to frequency changes than others. This can be achieved by setting the droop characteristic on those units to a lower value. The generator with the lower setting will pick up or throw off proportionally more load than the other generators on the system. Check with your supervisor for correct droop settings on your machines. Remember, the lower the percentage droop, the more sensitive is the governor. And oversensitivity can cause unstable operation and hunting of the unit. Now remember, all of the units which are connected to the power system are running at precisely the same synchronous speed. This is obvious because they are synchronized together, and the frequency is precisely the same at all points of the system. So how is it then that one unit may operate at, say, 100% capacity and another at 50%? Doesn't this mean that the unit with the greatest load is running faster? Well, beware of this trick question. Of course, it cannot run faster because, as we just said, the units are all synchronized together. So how does it then put out more load? Well, the answer is in the load angle, or power angle. This is the relative angle between the induced voltage due to the rotor and the terminal voltage, which is dependent upon the power system. This diagrammatic representation shows the situation at zero load. The rotor and the stator voltage are exactly in phase. If we wish to increase the load output from the unit, we add more energy to the prime mover. This initially accelerates the rotor so that it moves ahead in phase. There is now a power angle or load angle created between the rotor and the stator voltage. This in turn causes power to flow from the generator into the system. To further increase power output, we increase steam flow and so further increase the load angle, which in turn increases the power output. In each case, the rotor settles down to its new condition and continues to run at the new load angle. At maximum load, the load angle will probably be about 60 degrees. So now you can see if we have, say, 3 units in parallel on a common bus. The unit which is generating at 100% capacity will have a load angle of about 60 degrees. The unit at 50% output will have a load angle of about 30 degrees, and the unit at zero load has a load angle of 0 degrees.